The most dangerous signal that scientists watch for along the Cascadia Subduction Zone is not the earthquake swarms, not the dramatic offshore M6 events that make it briefly into regional news, not the shake alert notifications that rattle phones along the Oregon coast. The most dangerous signal is the absence of those things. Right now, the Cascadia Subduction Zone is giving scientists the signal they least like to see. During June, July, and August of 2026, the southern Cascadia Fault segment, the section running from the Mendocino Triple Junction in Northern California northward through the Oregon coast, recorded its lowest 3-month rate of microseismic activity since systematic monitoring of this fault segment began in 2003. The Pacific Northwest Seismic Network's Deep Tremor Catalog, which tracks the slow creep events that normally relieve stress from the transition zone between the locked and sliding portions of the fault, is running at approximately 40% of its expected activity rate for this point in the 14-month episodic tremor cycle. And the GPS stations monitoring ground displacement along the Oregon coast are showing eastward movement rates slightly above their multi-year average, consistent with a fault that is more completely locked than it has been in recent monitoring years. Fewer earthquakes, less tremor, more loading. This is not a coincidence of quiet data. It is a physics story, and the physics says the Cascadia Fault is loading. Drop a comment right now. Do you live in Washington, Oregon, or Northern California? Have you noticed that the seismicity maps have looked quieter this summer? And did you think that meant less to worry about? Tell me what your understanding of Cascadia's risk has been before today. If you want to be the first to know every time something like this develops, subscribe. It is completely free. A thumbs up helps enormously. Let us go for 5,000 likes so the algorithm puts this in front of the people in Seattle, Portland, and coastal Oregon who have been living in the Pacific Northwest without understanding what a quiet Cascadia summer actually means. Today we are going to break down the specific summer 2026 monitoring data, why the quiet is scientifically meaningful, and what the scientists who have spent their careers watching this fault are paying attention to right now. No guessing, no dramatizing, just the facts, the science, and the real stakes. Now, let us get into it. To understand why a quiet Cascadia is concerning rather than reassuring, you need to understand what normal Cascadia looks like, and why the departure from normal in the summer of 2026 is a departure in the wrong direction. The Cascadia Subduction Zone generates a background level of seismic activity that is lower than most active plate boundaries of its size, but it is not silent. Under normal conditions, the PNSN records between 2 and 5 magnitude 3 or greater earthquakes per month in the offshore portion of the southern Cascadia segment, generated by the ongoing motion of the Juan de Fuca plate against the overlying North American plate. These small events represent the occasional relief of stress concentrations along specific patches of the fault interface. Microfailures that release tiny amounts of the accumulated strain energy without triggering a larger rupture. More significantly, Cascadia generates a distinctive class of event called episodic tremor and slip. Slow, quiet, deep earthquakes that occur at regular intervals along the transition zone between the locked and freely sliding portions of the fault at depths of 25 to 45 kilometers. These ETS events are not felt by humans. They do not trigger shake alert. They are detected only by the borehole strain meters and GPS sensors that the Pacific Northwest Seismic Network maintains across the region. But they are important, because each ETS event releases a measurable portion of the stress accumulated in the transition zone and affects the loading state of the locked, shallower portion of the fault above. The 14-month ETS cycle is one of the most precisely characterized periodic geological phenomena in North America. Since the first systematic GPS monitoring of Cascadia began in the 1990s, the episodic tremor events beneath northern Washington and southern British Columbia have recurred at intervals of approximately 13 to 15 months with remarkable consistency. Each event migrates northward along the fault at a rate of 5 to 10 kilometers per day, producing a distinctive tremor signature in the PNSN catalog over a period of 3 to 4 weeks. The most recent major northern Washington ETS event, which I discussed in the earlier video on this channel about Cascadia's June 2026 offshore sequence, occurred in April 2026. The northern segment is therefore currently in normal inter-ETS repose, but the southern Cascadia segment is a different story, and that is the departure that concerns scientists. The southern Cascadia ETS, the sequence that normally propagates beneath the Oregon coast and into the northern California offshore region, was expected to occur in the spring of 2026 based on its most recent historical timing. That event did not occur as expected. The PNSN tremor catalog for the southern segment shows reduced deep tremor activity beginning in approximately February 2026, with the expected ETS window of April to June producing tremor totals at roughly 30 to 40% of the values recorded in the comparable windows of 2024 and 2023. The tremor is not absent. Small, scattered tremor events continue, but the organized, propagating episodic sequence that normally provides a several-week window of accelerated slow slip has not materialized. That changed fast when the background seismicity data was combined with the tremor picture. The offshore M3 and greater earthquake rate for the southern Cascadia segment, which normally averages 2 to 5 events per month, dropped to approximately 1 event per month during June, July, and the first week of August. Over 12 weeks, the total catalog contains only 3 M3 or greater events in the mapped southern Cascadia source zone. The historical 12-week record in this zone, extending back to 2003, shows no comparable 3-month period with fewer than 9 events. The summer of 2026 is, by that measure, statistically anomalous. The GPS confirmation came from 2 Oregon coast monitoring stations, one near Newport, one near Astoria, that show the current eastward movement rate of the Oregon coast slightly above the mean of the available multi-year record. Eastward movement of the Oregon coast is the expected response to the locked Cascadia fault, dragging the overlying North American plate in the direction of the subducting Juan de Fuca plate's motion. During ETS events, when the deep transition zone momentarily creeps, the GPS stations show a brief reversal of the eastward movement. The coast moves very slightly westward for a period of weeks. The absence of that westward reversal signal in the southern Oregon GPS record since February confirms that the southern ETS has not occurred. The coast has been moving east without interruption. The loading has been unrelieved. But here is the specific reason why scientists are cautious about overstating the significance of the summer 2026 quiet while simultaneously not dismissing it. A research paper published in the Journal of Geophysical Research in May 2026 by a team from Caltech, the University of Oregon, and the USGS identified a pattern in the Cascadia GPS and tremor record that they describe as inter-ETS loading variability. The observation that the amount of strain energy accumulated during each inter-ETS period is not constant. Some inter-ETS intervals show higher loading rates than others, and those intervals that show higher loading rates appear to be correlated with subsequent ETS events of greater total slip. The implication, which the authors stated cautiously and with significant uncertainty bounds, is that a longer than average inter-ETS quiet period may be followed by an ETS event of greater than average slip, and that a greater than average ETS slip event delivers a larger stress perturbation to the locked, shallower portion of the fault above. This does not predict an earthquake. It describes a physical mechanism by which the quiet summer could, if the pattern holds, lead to a more energetic ETS event in the fall, which would in turn affect the stress state of the locked fault. The chain of influence is real. The final link, from ETS to triggered megathrust rupture, remains scientifically unconfirmed. Now let us explain exactly what is happening physically beneath the Pacific Northwest this summer, and why the concept of quiet on a locked subduction zone has a very different meaning than it does on most geological features. The Cascadia Subduction Zone is a system in a state of sustained stress accumulation that has been ongoing since at least January 26, 1700. The date of the last major Cascadia rupture. In the 326 years since that rupture, the Juan de Fuca plate has continued moving northeast at approximately 40 millimeters per year. The locking at the fault interface, which prevents the two plates from sliding past each other, has accumulated the elastic deformation equivalent of that motion in the overlying rock. The total elastic strain energy stored in the locked Cascadia fault interface is enormous. It is the energy that, when eventually released, will produce the magnitude 8 or greater earthquake that the USGS assigns a 14% probability to occurring within the next 50 years. The small earthquakes and tremor events that normally populate the monitoring record are not release valves for this stored energy. They are orders of magnitude too small to measurably affect the total stored energy budget of the main locked zone. A magnitude 3 earthquake releases approximately 1 megajoule of energy in seismic waves, the equivalent of about a quarter stick of dynamite. A magnitude 9 earthquake releases approximately 200 trillion times more energy. No accumulation of magnitude 3 events is making a meaningful dent in the Cascadia stress budget. What the tremor and small earthquake activity does do is tell scientists that the fault system is in contact with its mechanical environment, that the plate interaction is producing observable microevents consistent with ongoing, normal plate motion. When those signals are suppressed, the scientific question is not, has the fault system stopped? It has not, the plates are still moving, but has the fault's mechanical coupling with its environment changed? A more completely locked fault. One where even the small stress concentrations that normally produce micro-earthquakes are being suppressed by a more homogeneous and complete locking of the interface, would show exactly the pattern being observed this summer. Fewer small earthquakes, less tremor activity, and continued or accelerated geodetic loading signals on the coast. The Cascadia Subduction Zone is a system in a state of sustained stress accumulation that has been ongoing since at least January 26, 1700, the date of the last major Cascadia rupture. In the 326 years since that rupture, the Juan de Fuca plate has continued moving northeast at approximately 40 millimeters per year. The locking at the fault interface, which prevents the two plates from sliding past each other, has accumulated the elastic deformation equivalent of that motion in the overlying rock. The total elastic strain energy stored in the locked Cascadia fault interface is enormous. It is the energy that, when eventually released, will produce the magnitude 8 or greater earthquake that the USGS assigns a 14% probability to occurring within the next 50 years. The small earthquakes and tremor events that normally populate the monitoring record are not release valves for this stored energy. They are orders of magnitude too small to measurably affect the total stored energy budget of the main locked zone. A magnitude 3 earthquake releases approximately 1 megajoule of energy in seismic waves, the equivalent of about a quarter stick of dynamite. A magnitude 9 earthquake releases approximately 200 trillion times more energy. No accumulation of magnitude 3 events is making a meaningful dent in the Cascadia stress budget. What the tremor and small earthquake activity does do is tell scientists that the fault system is in active mechanical contact with its stress environment, that the plate interaction is producing observable microevents consistent with ongoing, normal plate motion being accommodated at many small, local stress concentrations across the fault. The fault is, in a sense, speaking. It is saying, I am being stressed. I am generating microfailures in response to that stress. The stress is being distributed across many small sites rather than concentrating silently in a homogeneous locked zone. When those signals are suppressed, the fault stops speaking. The plates are still moving. The stress is still accumulating. But the fault is no longer distributing the incoming stress across microfailure events. It is storing it more uniformly. A fault that stores stress uniformly, where the entire interface is locked and quiet rather than a patchwork of locked zones with microevents scattered between them, is a fault building toward a more spatially coherent and potentially more energetic eventual release. This is the physical reasoning, grounded in the mechanics of elastic media and fracture theory, behind the concern that a quiet Cascadia is not the same as a safe Cascadia. The ETS events add a second layer to this physics. In the transition zone below the locked interface, where temperatures and pressures are high enough that the fault rocks deform plastically rather than failing brittly, slow slip occurs at intervals because the fault rocks cycle between periods of velocity strengthening and velocity weakening behavior. During an ETS event, the transition zone briefly accelerates its creep, delivering a stress pulse upward to the overlying locked zone. That stress pulse is small relative to the total stored energy budget, but it is measurable, and it has been observed in GPS and strainmeter records to cause minor increases in small earthquake activity in the locked zone above in the weeks following major ETS events. The locked zone responds to the ETS perturbation. When the ETS events are suppressed, the locked zone is receiving fewer perturbations, fewer microfailures are being triggered, and the stress is accumulating more uniformly and more completely. The closest historical parallel that scientists point to is the Japan Trench in the years preceding the March 11, 2011 Tohoku earthquake. Research published after Tohoku identified a period of anomalously reduced seismicity on portions of the Japan Trench in the decade before the 2011 rupture. The Tohoku rupture zone appears to have been more completely locked, generating fewer micro-earthquakes on the locked interface in the years preceding the rupture than it had been in the previous decades of monitoring. This is a studied and debated body of research. Not every seismologist agrees that the pre-Tohoku quiet was statistically significant, but it is the reason that the Cascadia summer 2026 quiet is not being dismissed. Scientists have seen what a quiet, well-locked, loading subduction zone can do when 326 years of accumulated energy is eventually released. The human stakes of the Cascadia loading are concentrated in specific ways that depend on where along the Pacific Northwest coast someone lives and what they are doing there. For coastal communities within the zero warning zone, those sitting directly above the locked fault interface, where the shaking from a full Cascadia rupture would arrive before any shake alert system could detect the distant earthquake and transmit a warning. The summer 2026 quiet is not something that changes their immediate risk. Their risk does not increase because the ETS was disrupted this summer. Their risk is defined by the structural state of the fault interface and by the 326 years of accumulated strain. That risk was the same in the summer of 2025, and it will be the same in the summer of 2027. What the summer quiet does change is the researchers' assessment of where the fault interface's stress state sits within its loading cycle. The human stakes of the Cascadia loading are concentrated in specific ways that depend on where along the Pacific Northwest coast someone lives and what they are doing there. For coastal communities within the zero warning zone, those sitting directly above the locked fault interface, where the shaking from a full Cascadia rupture would arrive before any shake alert system could detect the distant earthquake and transmit a warning. The summer 2026 quiet is not something that changes their immediate risk. Their risk does not increase because the ETS was disrupted this summer. Their risk is defined by the structural state of the fault interface and by the 326 years of accumulated strain. That risk was the same in the summer of 2025, and it will be the same in the summer of 2027. What the summer quiet does change is the researchers' assessment of where the fault interface's stress state sits within its loading cycle. What the Tohoku parallel adds to this picture is the most important cautionary note in the entire 2026 monitoring story. In the years before the March 11, 2011 magnitude 9.0 earthquake off the coast of northern Honshu, Japan, a body of research subsequently published noted that portions of the Japan Trench in the eventual rupture zone had been generating fewer small earthquakes than adjacent sections of comparable fault area. The fault was being stressed. The Pacific Plate was subducting beneath northern Japan at a rate of 80 millimeters per year. But the stressed zone was not distributing the incoming stress across the normal density of microfailure events. A 2023 paper in the journal Earth and Planetary Science Letters specifically analyzed the spatial distribution of Japan trench seismicity in the decade preceding the Tohoku earthquake and found that the eventual rupture zone was statistically quieter than adjacent segments at the micro-earthquake level. The interpretation, which remains debated, is that the eventual Tohoku rupture zone was more completely locked, more uniform in its stress distribution, than adjacent sections in the final decade of its loading cycle. The uniform locking allowed a more spatially coherent rupture when the eventual failure propagated. The Tohoku magnitude 9 covered 450 kilometers of fault strike and produced one of the largest tsunamis in Japanese historical memory. The pre-Tohoku quiet was not the warning that it might have been. The scientific community has been asking, since 2011, whether better interpretation of the quiet would have provided additional lead time for the public communication of elevated risk. The summer 2026 Cascadia quiet is not Tohoku. The Cascadia fault has been locked since 1700, and the monitoring record is too short to identify a baseline against which to define departure. But the Tohoku comparison is why the summer 2026 quiet is not being dismissed. But for the inland cities, Seattle, Portland, Tacoma, Eugene, the relationship between the fault's stress state and building preparedness is what actually determines the outcome for human life. The seismic codes for new construction in Washington and Oregon have been updated progressively since the 1980s, driven in part by the recognition that Cascadia is a megathrust fault capable of magnitude 9 events. Buildings constructed after the adoption of modern seismic codes in the 1990s are designed to withstand the expected ground motions from a Cascadia event significantly better than older construction. But the Pacific Northwest's building stock is a mix of the old and the new. Unreinforced masonry buildings from the early to mid-20th century remain in use throughout both cities' commercial and residential cores. The number of concrete tilt-up structures built before modern seismic design requirements is significant. The building stock that will bear the consequences of a Cascadia rupture is the full range of the Portland and Seattle built environment, from post-millennium high-rises designed for seismic loading to 1920s brick commercial buildings that were designed for gravity loads and weather, not lateral seismic forces. Portland, Oregon, has been particularly active in its seismic assessment of the existing building stock. The city conducted a comprehensive survey of unreinforced masonry buildings in the late 2010s and has been implementing a mandatory retrofit ordinance for the highest risk structures. The program is real and the progress is measurable. But the scale of the building stock and the funding required to retrofit or demolish the most vulnerable structures means that the work will not be complete before the next Cascadia earthquake arrives, regardless of when that earthquake comes. What scientists at the Pacific Northwest Seismic Network and the USGS Cascades Volcano Observatory are monitoring in response to the summer 2026 quiet is a specific set of additional measurements designed to test whether the quiet represents a change in the fault interface's mechanical state or simply the natural variability of a system that has never been monitored through a complete loading-to-rupture cycle. The GPS array along the Oregon and Washington coast will continue to be the primary indicator. If the eastward movement rate, currently slightly above average, were to accelerate significantly, it would suggest that the loading rate itself has increased, possibly due to a change in the deep plate coupling. If the eastward movement rate suddenly shifted to a westward reversal without a prior ETS signal, it would suggest that the locked fault interface had experienced a previously undetected slow slip event. Either change would warrant an updated assessment. The current rate is elevated, but not dramatically so, consistent with the absence of ETS stress relief rather than a fundamentally changed loading regime. The borehole strainmeter network is also being watched for any signal of deep, slow slip at the transition zone that the surface GPS network might be too coarse to resolve. The EarthScope borehole instruments embedded in the rock beneath the Olympic Peninsula and the Oregon Coast Range are sensitive enough to detect strain changes equivalent to millimeter-scale ground displacement integrated over a large area. If a partial ETS, a slow slip event affecting only a limited along strike section of the transition zone, were to begin, the strain-emitters would detect it days before the GPS network would show a clear reversal signal. Keep an eye on the PNSN tremor map in the fall of 2026. If the overdue southern ETS begins in September or October, the tremor migration pattern visible in the public PNSN tremor catalog will be the first public signal that the loading pause has ended and the transition zone has begun its slow episodic release. A larger than average ETS slip, if it occurs, would not threaten communities directly. ETS events occur too slowly and too deeply to generate hazardous ground motion. But a larger than average ETS slip following an extended quiet period would be the physical realization of the mechanism that the May 2026 Journal of Geophysical Research paper described. The quiet summer's stored energy being released not in a megathrust earthquake, but in an energetic slow slip event. Here's what the science leaves us with. Does the summer 2026 quiet mean that a Cascadia megathrust earthquake is more likely this fall than it was last year? Scientists currently have no evidence supporting that conclusion. The probability of a major Cascadia earthquake in any given year remains the same before and after the summer 2026 quiet. The quiet is within the range of observed variability for the Cascadia system, and no current monitoring signal indicates that the fault interface is approaching rupture. The summer quiet has not changed the USGS's 14% in 50 years probability estimate. It has not changed the scientific community's consensus that Cascadia is in the middle of its interseismic loading period, not at its end. What the summer quiet has done is provide a more complete picture of the current state of the fault interface's stress distribution. And that picture is consistent with a fault that is more completely locked than the recent monitoring period's average. More completely locked, in the physical language of elastic strain, means more stored energy per unit of fault area. More stored energy per unit of fault area means a more energetic release when the rupture eventually occurs. The quiet is not a warning of imminent rupture. It is a data point about the total energy budget that is still accumulating 326 years after the last release. If you live in Washington, Oregon, or Northern California, the summer 2026 quiet does not change what you should do to prepare for Cascadia. The preparation is the same whether Cascadia is generating its average background seismicity or running quiet. Know your tsunami inundation zone and evacuation route. Know the drop cover hold-on protocol for when the shaking starts. Have a go bag ready with water, food, medications, and documents for 72 hours of self-sufficiency. And if you live in the coastal zero warning zone, Seaside, Astoria, Cannon Beach, Newport, Lincoln City, Pacific City, the preparation is more urgent, not because the summer has been quiet, but because it has always been urgent, and the summer quiet is another reminder that the clock has been running since 1700. Drop a comment and tell me, have you been watching the PNSN seismicity maps this summer? Have you noticed the quieter than usual record? Tell me what you thought it meant before watching this video. And let us go for 5,000 likes so the algorithm puts this in front of the people in coastal Oregon and Washington who need to check the evacuation route maps today, not next week. See you in the next one.